in the last, so let me go ahead. So in the last class, we just talked about that if we have any mathematical function Tx, it can be a differential equation or anything, then it is said to be linear. It is said to be linear in X if it satisfies two properties. First property is that T of addition property, T of x1 plus x2 is equal to T of x1 plus T of x2. And the second property is that if we have some scalar lambda, then T times T of lambda x is nothing but lambda will just come out n. So any expression Tx, if it satisfies these two properties, then we say that that expression Tx is linear in X. Okay. So this property is called the property of addition, and this is called the scalar multiplicative property. So linear combination is nothing but it is a combination of these two properties. So suppose let us have, if we have v1, v2 up to vn, n number of vectors, and w is another vector. So let us suppose that v1, v2, vn and w, and there are some vectors in some real vector space V, then we can write W as the linear combination. W can be written as the linear combination of V1, V2 up to Vn, because we have n number of vectors. That is, mathematically we can just write it W is equal to lambda 1 V1 plus lambda 2 V2 plus up to lambda n Vn, where lambdas are some scalars. Lambdas are some scalars. And V1, V2, V3, they are also. So this is a fundamental concept. This is a fundamental concept of vector space. Linear vector space. Concept of linear vector space. Theory. Why? Why it is fundamental? It is because it is made up of addition and scalar multiplication. Addition and scalar multiplication, which are the two fundamental properties of linearity. So these two fundamental, because we know that these individual terms are nothing but the scalar multiplicative term, and we just add these, so we'll get something like this. So this is one of the most fundamental property, that any vector W can be written as a linear combination of the other vectors V1, V2, V3, which belong to some vector space V. So let us suppose, for example, we have some set S of all triples. Triples means we have like three components X, Y, Z, such that X plus Y plus Z is equal to 0. And we have another set of vectors called U. Suppose U is 0, 1, minus 1. V is another set of vector, V 1, 0, 1, minus 1, 0, 1, and W, which is 1, minus 1, 0. So, and this UVW also belongs to the same vector space V. U, V, W also belongs to vector space V. Okay, so we can write X, Y, Z as a linear combination of these vectors. And by solving, I'm just writing it like, you can just see 0, 1 minus 1 plus Z minus X by 3 minus 1, 0, 1 plus X minus Y by 3 1 minus 1, 0. So if you just add this, you'll get this. So any vector as x, y, z can be written as a linear combination of these triples, like 0, 1, minus 1, minus 1, 0, 1. So this, so in this way, for this three-dimensional vector space, because you have three components, these form the basis of the function. Basis means any, using this basis, any linear combination of this basis will give you the any other vector which belong to that vector space. So now, using this expression, one of the most fundamental concepts which comes in the linear vector space is linear independence. Linear independence or dependence, whatever it is, they are just opposite each other. So we say that vectors v1, v2 up to vn are linearly independent we say that these vectors v1, v2 up to vn are linearly independent if the only solution of the equation, we have some equation lambda 1 v1 plus lambda 2 v2 up to so on and so forth up to lambda n vn. We have n dimensions. So if the only solution of this equation is given by lambda 1 is equal to lambda 2 is equal to up to lambda n, they all are equal to 0. So we have only trivial solutions. That is, the only solution of this equation is that all the scalars are equal to 0. If it happens like this, then we say that these vectors v1, v2 up to vn are linearly independent. One of the example of this linear independent vectors for like in usual Cartesian coordinate, you have three coordinate system x, y, z represented by I cap, j cap, k cap. So they all form linearly independent vectors. Okay, so in the same way, they are orthogonal to each other also. So in the same way, we say that if the only solution of this equation is that all the scalars are equal to 0, then we say that it is linearly independent. Else, we say if suppose any of these scalars is not equal to 0, then we say that these vectors are linearly dependent. So this is one of the like basic concept. For example, I took these two u and v. So let us check whether u and v are linearly dependent or independent. So we know that u is given by 0, 1 minus 1, and v is minus 1, 0, 1. So we have to check whether these two vectors are linearly dependent or independent. So what we will do is that we will just try to use this equation lambda 1 v1. So we have lambda 1 u plus lambda 2 v is equal to 0. And now we'll try to find out that what are these coefficients lambda 1 and lambda 2. So okay, so we'll just write lambda 1 u is nothing but 0, 1, minus 1, and v is minus 1, 0, 1. So just solve this. So lambda, so first is, this is 0, lambda 1 into 0 plus minus lambda 2 is equal to 0. Similarly, you can lambda 1 is equal to 0 and lambda 1 is equal to lambda 2. So I've just solved this like that. So what the solution which you are getting is that both the scalars are lambda 1, lambda 2 is equal to 0. Hence, it means that u and v are linearly dependent. Independent. That is, there is no relation through which we can connect u and v. There is no relation through which you can have a equation between u and v, so that they, for example, you cannot write that u is some say a times v or some constant. So you cannot establish this type of relationship. So they're linearly independent. Is this clear, like what I've told till now? I will solve more examples so it will be much clearer later also. So you have to basically, if you have to find in any question, if you have to find whether they're linearly independent, so you have to just find the scalars and see that if they are 0, then you can just say that they are linearly independent. If they are not 0, you're getting some kind of equation which is not trivial, then you can say that they are linearly dependent. So let us have another example. Example 2. So maybe I'll start with another page only. So let us assume that we have three functions, f of x. Let us take trigonometric functions. F of x, which is sine x. G of x is sine of x plus pi by 4. And h of x, which is sine of x plus pi by 2. So we have these three functions, and this x belongs to some real space for all values of x. So we have to find out whether these three functions are linearly dependent or not. So what are they? So we'll use a similar approach. So let us assume that we have three scalars. Lambda 1, lambda 2 and lambda 3. Okay. So for linear dependence, if they are linearly dependent, these three functions, for linear dependence, not all lambda i's will be equal to 0. And for linear independence, all lambda i's. So if we are able to prove that, not all lambda is equal to 0, then we can say that okay, these three functions are linearly dependent. So we can just write the equation. So our equation is lambda 1 times fx plus lambda 2 times gx plus lambda 3 times hx is equal to 0. And lambda 1 times fx is nothing but sine of x. This is sine of x plus pi by 4. And this is, sorry, lambda 3 times sine of x plus pi by 2. Now we know that this can sine a plus b. Sine a plus b is sine a cos b plus cos a sine b. Most of you must be knowing this in high school maths. So we can write this as sine of x into sine of pi by 4. Sorry, sine a cos b, I think. So, that's cos x sine pi by 4. And this is nothing but sine 90 plus x is nothing but cos of x. So we can just write this as lambda 1 sine x. Cos pi by 4 sine pi by 4 is 1 by root 2. So root 2 will come out. So we have sine x plus cos x. plus lambda 3 cos x is equal to 0. Now we can just collect sin x term together. So it will be lambda 1 plus lambda 2 by root 2 sin x. I've taken these two. And then lambda 2 by root 2 plus lambda 3 of cos x is equal to 0. Now in order to satisfy this equation, there is one way through which you can do. If the coefficients of the sin x and cos x both are 0, then we'll automatically have this LHS is equal to 0. So one of the solution is that lambda, if we take lambda 1 is equal to 1 and lambda 2 is equal to minus root 2 and lambda 3 is equal to 1. If we just take these three cases, then your lambda 1 is 1, 1 plus minus root 2 by root 2. So 1 minus 1, 0. So this term will go out. Similarly, minus root 2 by root 2 is minus 1. Minus 1 plus lambda 3 is 1. So this term will also go out. So if we take this combination, we have found three values of scalars, 1, 1 and minus root 2. And for these values of scalar, we are able to satisfy this equation. So hence, here we can prove that lambdas are not equal to 0. So we can have non-trivial solutions. These are called non-trivial solutions. That is for some value of lambda 1, distinct value of lambda, we can satisfy this equation number 2, suppose. And hence we can say, since these scalars are not equal to 0, they fx, gx, and hx, they are linearly.
Sir,
Yes, hello.
can you tell again why lambda 1 equals to 1? I couldn't hear it. There was loud noise.
Oh, okay. No, I'm just trying to see. We have to try to figure out that whether we can have some non-trivial solution. Non-trivial solution means lambda value is not equal to 0. So we can see if we just put lambda 1 is equal to 1 here. I'm just supposing if lambda 1 is 1 and lambda 2 is minus root 2, then this coefficient will become 1 minus 1, 0. So this term will vanish out. Similarly, the coefficient of cos x will also be minus 1 plus 1. This term will also vanish out. So for these values of lambda, you are able to satisfy this equation number 2. So and this value of lambda is not equal to 0. So what I mean to say is that you are able to prove that you have some values of lambda which are not equal to 0. And for that value of lambda, you are able to satisfy this equation. And hence, these functions are linearly dependent. Because,
Okay, sir. Thank you.
yeah, so that's the only thing. So basic thing is that you have to see this. Yeah, you have to focus on these two lines. For linear dependency, not all lambdas are equal to 0. For linear independence, all the lambdas will be equal to 0. So this is one of the basic. In short, if you want to remember that how to find this, so you can just. Okay, so now before moving to solving, I will solve a couple of gate questions. So before solving that, I think I forgot to tell about dimensions. So similarly, what are dimensions in vector space, real vector space? So as I already told that if we have set of vectors v1, v2 up to vn, and if they are linearly independent, if we have set of vectors v1, v2, vn, and they are linearly independent, and they belong to some vector space v, then we say these vectors v1, v2, vn, these vectors forms basis, and the number n is called a dimension. So if n is suppose 3, suppose v1, v2, v3 in last case, suppose if we have n is equal to 3, then we can say that, okay, and if all V1, V2, V3 are linearly independent to each other, then we can say, okay, then V1, V2, V3 form the basis of a three-dimensional vector space. Similarly, if n is equal to 5 and V1, V2, V3, V4, V5, they are linearly independent, then we can say that, okay, these vectors are form the basis of five-dimensional real vector space, so and so forth. So now I will solve, it is clear, this point? Hello?
Yes, sir.
Yes, sir.
Okay, so this is simple question. So maybe I will solve and I will ask you also. You people can also solve this. And the question is that it appeared in GATE 2005. So they have given four column vectors, four vectors in the form of column matrix that U1, U2, U3, and U4. And then they have just asked that which pair among these four options forms a linear independent pair. So you can just, I will just give you 5 minutes. So maybe less than that. So you can just solve this, and if you're getting the answer, you can just type in the chat box that what is the correct answer for this. Is it fine? Just follow these steps. You just have to do these things. You have to take two scalars and then you have to check whether these, by forming equation, you have to check whether all lambdas are equal to 0 or they are not. If all of them are equal to 0, then it means they are linearly independent. Okay, so slight correction. The question is you have to find linear dependent pair. Linear dependent pair. Sorry for the typo. There was a typo. So you have to find that which one of these four pairs is linearly dependent. Okay, so I'm getting a couple of people have already answered. Good. Itraj and Santuna. Okay, so I think I can also solve. It's not a difficult task. So you can just lambda 1 u1 plus, you can just check this. For example, first option is lambda 1 u1 plus lambda 2 u2 is equal to 0. So you can just 1 to 1 plus 3 minus 5, 1 is equal to 0. So what we'll get is lambda 1 plus 3 lambda 2 is equal to 0. 2 lambda 1 minus 5 lambda 2 is equal to 0. And lambda 1 plus lambda 2 is equal to 0. So from this equation, you can get lambda 1 is equal to minus lambda 2. And put this in first equation, then you will get minus lambda 2 plus 3 lambda 2 is equal to 0. So this lambda 2 is equal to 0 and hence lambda 1 is equal to 0. So obviously you're getting both the scalars are equal to 0. That means that u1 and u2 are linearly independent. Similarly, if you also solve for b or c, you will see that both the scalars are equal to 0. So these three are for sure linearly independent to each other. But if you solve the fourth pair, that is 2, 4, minus 8, so lambda 1, 2, 4, minus 8 plus lambda 2, 3, 6, minus 12 is equal to 0. So get three equations. So 2 lambda 1 plus 3 lambda 2 is equal to 0, first equation, equation A. Second is 4 lambda 1 plus 6 lambda 2 is equal to 0, which is nothing but take 2 common, so it will become 2 lambda 1 plus 3 lambda 2 is equal to 0. And similarly, third will be minus 8 lambda 1 plus minus 12 lambda 2 is equal to 0. So this will also minus 4 you will take common, so this will become So all these three equations are same, 2 lambda 1 plus 3. So we don't have any trivial solutions. So we don't have solutions is lambda 1, lambda 2 is equal to 0. So, but we see that the only solution is that this kind of solution which we are getting, which is not equal to 0. For example, lambda 2 can be 1, 2, 3, anything. So hence we can see that this vector mu3 and mu4 are linearly dependent, and the equation, the relation between these two vectors are that mu3 is nothing but equal to minus 3 by 2 times mu4. So this is the relation between these two vectors. So they are related to each other. They are dependent on each other. So hence this way you can arrive at this question. So yes, most like three people have already answered that D is the correct option. So this is simple way through which you can just solve and see that, find the answer. So I think it's clear to. Does anyone have any doubt in this?
No.
Okay. Yeah. So now I will solve another question. It came in GATE 2020. So the question is they have given three vectors 100, 110, and 111, and they say that they belong to some vector space, three-dimensional vector space RQ, and then they have asked that which one of the following is correct. So they're given four options that S is a linearly dependent set. So these three vectors form a set S. So they have asked that whether these whether this set is a all the vectors belong to this set are linearly dependent, or they form an orthonormal set, or they form basis, or they satisfy this equation. So there is another thing, a shortcut kind of method, because you can always solve this by using this approach by forming this lambda 1 times. You can just check that lambda 1 times C1 plus lambda 2 times C2 plus lambda 3 times C3 is equal to 0, 0, 0. And then you can find that whether they are linearly independent or not. But uh, there is another way, a little shorter way through which you can find. So I will just say how to check linear independency for three-dimensional like real vector space. Here we have three-dimensional real vector space. So I already told that if v1, v2 up to vn, if they are linearly independent, then they form a three-dimensional. They belong to some three-dimensional vector space. And v1, v2, vn, they are called the basis vectors, because any linear combination of these vectors can, that any other vector belonging to this vector space can be expressed as a linear combination of these vectors. And n is nothing but a dimension. So here we have three dimensions, because we have a three-dimensional already given in the question. So n is 3. And we know that if we have any three-dimensional structure, so if we have any vectors which span in three direction, so the volume occupied by these vectors would be finite, because any 3D structure has some finite volume. And we know that what I want to tell is that if three vectors are linearly independent, in some vector space V, like they belong to some vector space V, then there would be some finite volume occupied by these vectors, or basis vectors more appropriately. And we know that volume occupied is nothing but it's given by scalar triple product. So here we have three vectors E1, E2, E3. So their scalar triple product is nothing but E2 cross 3. Here is three vectors. And this is given by the determinant. So we can just write 1, 0, 0. So you can just one, 0, 0, 1, 1, 0, and 1, 1, 1. Just find the determinant. So the determinant will be what? 1 minus 0 plus 0 plus 0. So I know everyone must be knowing how to calculate determinant of the method. So determinant is 1 and this determinant is not equal to 0. That means that they occupy a finite volume. So we can say the given vectors are linearly independent, and as I've already told that if they are linearly independent, then they form basis of three-dimensional vector space R3. So yeah, so I think first option is wrong because if they were linearly dependent, then this determinant would be equal to 0. Determinant 0 means the volume is 0. Volume 0 means this is not a 3D structure, it is kind of 2D, two-dimensional. So like what I meant to say is that V1, V2, V3, if the determinant is not equal to 0, that means it's not a linear independent set. Any vector, any one vector here can be represented as a linear combination of other two. So hence in this way you can just find the this scalar triple product. If it's coming out equal to 0, that means they are linearly independent. And if the scalar triple product is not equal to 0, that means they are linearly independent. Okay, so so option C is right, and then option D is also, suppose they have given the question that which one of the following is correct. So you can just take option C. But if it was a multiple select question, then you have to also check each every option. So you can also check option D also. I think option D is summation I is equal to 1 to 3 EI. So it's nothing but in Cat and Brown notation they have just tried to. So this Cat notation is in column vector, so its Brown notation will be row. So it will be 100 times 100 plus 110 110 10 plus 111 times 111. These all will give 3 cross 3 matrix because 3 row 1 column, 1 row 3 column. So these all will give 3 cross 3. And when you'll add this 3 cross 3 matrix, you'll get something 1 1 or something like that, which is not equal to 1 0 0 0 1 0 0 0 1, which they have given in the option. So option D is also not. Option D is also not correct. Correct. So in this way, the only option which is correct is option C.
Sir, how we will check the option B, orthonormal conditions?
For orthonormal, you know that if any two vectors are orthonormal, their dot product is 0.
Oh, okay.
So using that, you can just find. You just multiply this. You not get 0. You will just
So
multiply.
orthonormality already have to check dot product 0.
No. If two vectors, they're like orthogonal to each other, then their dot product is what?
So that is the condition of orthogonality, na?
Yeah, that's right. So orthonormality condition is also related to that. It's more detail in that. So right now, as far as I can remember, you can just check this using this thing. And
Sir,
So
if they are orthogonal, we would have to check if they are normalized or not to see whether they are orthogonal or not. But these are not orthogonal at all, so we can just do that by this.
okay, yeah. Yeah, these are not normalized at all because in order to normalize it, yeah, you have to do it.
that's why I asked, because three vectors are not normalized.
Mm-hmm.
That's why I asked how to check orthogonal, because I know orthogonality means dot product is 0.
Yeah. Okay. Mhm. So
And for third option, basis only, we have to check the linearity conditions.
yes, you have to just check the linearity condition, and then because as I have already told, if they form linearly independent set of vectors, then they form the basis.
Okay.
Yeah.
Means they are linearly independent, they form basis.
Yeah, if they're linearly independent, then it means that all these three vectors, like any linear combination of this lambda 1 e1 plus lambda 2 e2 plus, you take any linear combination, will give another vector w or something which also belong to this vector space. So
Okay,
It should
thanks.
also span the space.
yeah, they should also span this space. So, and so these are a couple of the questions which I solved. This, and I also solved some more questions in the last session, like in the previous first phase of this. So you can also, I think I don't see many questions from linear independence in the GATE exam. It doesn't, not many questions come, but when it comes related to this only linear independence, orthonormality, and this basis and all. So, like if I am not wrong, then there's some question 2018 also which came. I don't have it right now. But I've shared with you that first phase PPT also. Okay. So there I have solved two more questions related to GATE. These two questions were remaining, so I solved. So okay, so I think broadly, like I've covered whatever I wanted to do from this linear vector space. I'm not trying to go into very detail and those things because the main motive of this class is to solve GATE questions and to set a background related to solving those GATE questions. So if you have any doubt or if you want me to cover some more topic, then you can always tell me. So the later part of this session, like in the last few lectures, I will cover those extra topics and some questions related to that. Someone is telling something. Hello.
Sir, option C, could you please explain again?
Okay. So here what they've asked is that they're given three vectors and E1, E2 and E3. And then they have asked us that these four options, which one of the four options is correct. Then first of all, anytime you get this type of questions, you first check whether they're linearly dependent or independent. And in order to do that, and if you're solving for a three-dimensional space, then you just have to find the scalar triple product formed by these vectors. So these are like three vectors. So you just found the matrix out of these three vectors. That is 1, 0, 0, 1, 1, 0, 1, 1, 1. So each will go. So and when you find the determinant of the matrix, so this determinant of the matrix or scalar triple product is nothing but it gives the volume occupied by these vectors. And if it and the volume occupied by the vectors, if it's coming out to be equal to not, if it's not equal to 0, that means that these set of vectors have 3 degrees of freedom. Like what I want to tell is that they're linearly independent to each other. By linearly independence means they cannot be represented as linear. Like we cannot write V2, or suppose we cannot write E2 as a linear combination of E1 and E3. We cannot do that.
Yes, sir. But the S is a basis of R cube that I have doubt.
Okay, basis. So once you have established that these three vectors are linearly independent, then it means that you can write using these three vectors whatever linear combination you take, as I told in the last class. Like if we have v1, v2, vn and they are linearly independent, then their then we can write. Let me write another. Then any of the vector can be expressed as a linear combination of v1, v2, vn. Okay, and when you can write any linear combination of these vectors, then these vectors are called the basis vectors. Or maybe I will go back to the last class. I think I tried to explain basis. Yeah. So in the last class, I explained what is basis. So basis in linear vector space consists of a set of linearly independent vectors called basis vectors, and any other vector can be written as a linear combination of these basis vectors.
Okay, so it is a linear independent vector only.
Yeah, so if we have established that these vectors, any vectors are linearly independent, that means those form the basis vectors.
Okay, sir. Could you please share the notes after the
Yeah,
class?
I will share the notes.
Okay, sir. Where we can find that?
What's the name? Like
Sir, Anuj.
Anuj.
Yes.
First time you're joining class.
Yes, sir. I am joining this class first time.
Okay, so to all of to those people who have just joined today, you can just type your email ID in chat box. I will add you to a group. I have Outlook group, so I will add you there, Microsoft Outlook group, and I'm sharing the. I've already shared the PPT and all those things there. So those of you who are new, you can just type your chat box, your email ID in the chat box. So if 3 people have already typed, Rupesh, Shyam, and Esmohana. And in the next lecture, I will be coming to differential equations. Okay. Any more doubt, like any questions? Okay, so I don't see any questions here. So in that case, we can like close today's class. So that's thank you for joining.
Thank you, sir.